Good morning, everyone. So today we continue our lecture. Chapter 3 is conservation of energy. So like we discussed before about energy that and mass, they are both are conserved. And then like how we apply the conservations of energy to calculate the total of energy in thermodynamics or in the process engineering. So in this case, if you take one example of the energy, for example, like if we drive the car and then you use the fuel, like we can calculate like how much the total of enthalpy, internal energy. So what's the relation of the internal energy and then enthalpy? This is what we would like to discuss in this chapter. And also like what's the applications in the some problems in the thermodynamics, how to calculate and then combine all of them into the one solutions. So basically, if you go to the chapter 3 about the calculations of the energy, it's almost similar like the mass balance, and this is energy balance. We can also apply like some system like open system, closed system, adiabatic. So this is why we discuss in the chapter 1. So I hope you still remember about the definitions. Like open system, you have mass in, mass out, energy in, energy out. However, for the closed system, you don't have mass in, you don't have mass out, but you have energy in and energy out. So in this case, we start to discuss about chapter 3. Okay, so from the name, like we discussed about the conservation. So conservations, it means that the energy it's conserved, yeah, or the principle in physics that states the energy can neither be created or nor also destroyed. So in here, like energy is conserved. So for example, I have 1000 kilojoule or 1000 joule per mole in, that they will be equal to the 1000 joule per mole in out. So the total of energy in the system by itself remains constant. So this is what we discuss also in the mass balance. Like for example, chemical, like we eat the ice cream, so like all of metabolism in our body, it's have the chemical process. So this chemical process, they will convert into the motions like we do for moving, you go to for the sport. This is all is metabolism processes. That's why if we don't eat, for example, like some hours, and then you feel like so weak, our body is very weak because we don't have energy. And the other is radiant from the sun. So radiant from the sun, we use as a photocatalysis for the plant, yeah. So we use the, if you saw like the trees, so they have the photocatalysis process, or in here you have you need the radiant from the suns, and also like the chemical fuel. We use the fuel for the motorcycle, for the car, so they can change or convert the energy into the motions. And also for the electrical, we use the electrical to heating. We use electrical to let's say like to have to convert into the light. We use the electrical also for the motion for the fan, so for the AC. So this is like kind of the energy transformations that may have in the our daily life. So basically, like if you discuss about thermodynamics, it's not only about calculations, but thermodynamics, it's happen in daily our life, yeah. So even the natural process, like if you go to the Peito in the hot spring, so this is natural, it's because of heat, and then they have like a hot water, so you can use the hot water for many applications. So in this case, like how we calculate the conservation of energy itself. So conservation of energy is basically it's from Q, yeah. This is Q, the conservation of energy. So we have the Q. So Q in here, actually this is you can write as theta. Theta equal to the U plus M, and then here we have the V squared divided by 2 plus in here we have the Greek letter, yeah, for the potential energy. So I think this is because the PPT, so I'm sorry, the symbol it should be in here, it's equal to the, let's say for the omega, yeah. So in here we have the theta is equal to the U plus mv power of 2 divided by 2 plus omega. So in this case, if you check that U, it means that the total energy, and then we have V power of 2 divided by 2. This is kinetic energy per unit mass. So if you would like to calculate with the molar energy, so in here you can have the N, or in here you can use the M. It's both are the same. So you just need to indicate this is the cap or underline like we discussed before. So here we can replace with the potential energy per unit mass. Then this is theta, it's equal to the theta generations. Yeah, I change to theta. This is equal to B0. So in here energy is a conserved properties. So it means that the total it's equal to B0. So we don't have the, if you supposed to be have in here, you don't have any generations because the energy is a conserved, the same like the mass balance. We also have is a conserved properties. Then we can take that for the energy balance equations, we have d divided by dt, u plus m v power of 2 plus divided by 2 plus omega. So in here it means like in the systems, yeah. So in the system we have the rate at which energy enter to the system minus the rate at which energy leave in the system. So you have here, for example, this is in the boundary line. This is the red boundary line. This is system. And then we have here the work positive and then go out its work negative. We can indicate the negative it's for the leave and then positive it's for the enter. Like we discussed in the chapter 2 and chapter 1, it's also similar, yeah. So what is the M? M it's mass, and then the Q it's the total heat. So all of this in it's equal to be out if you have the steady state system, and then if you don't have, if you have the unsteady, it means like they are function of the time. So currently, like how we going to solve the problem in the energy flow accompanying mass flow? Because here we discuss about the mass flow, and then we have the sigma mk u plus v power of 2 divided by 2 plus omega. So in this case you have the mass, and that's why here we use the cap. So if you supposed to be use the n, we also can change this one become nk. In here u underline plus v divided by 2 plus, yeah, so here omega, so here you can k, yeah. So in this case we can use the underline, but for the m we can use the cap. So about the heat it means that q dot, why in here we have dot it represents about flow. So if you supposed to be calculate about mass flow, so it's m dot. For the heat it's q dot, then equal to sigma qj. J it means it's for the system. And in this chapter also we discuss about work, like in the chapter 1 we discussed before. So we have the soft work, and then for the workforce, yeah. So WF and then WS. So they are totally different. If you calculate WS itself, it means that the mechanical energy flow that occurs without a deformation of the system boundaries, including electrical. For example, you have the turbine. This is all its WS. Turbine, pump, yeah, this all it's equal to the soft work. And then WS itself, they have two signs. If you have the negative sign, it means that the system do works to the surrounding, but WS positive, it means surroundings do work on the system. Actually, this one depends on the textbook. Some of the textbook, they will use negative and the positive with the different meaning. However, in this textbook, we use this, we define that WS negative, it means system do work to the surrounding. Yeah, so remember that we discussed in the chapter 1 about the system and boundary and the surrounding. It means that any kinds of the outside the system, this is we call it surrounding. So the system itself, it was the whatever enter like mass Q or the N, but the line, that the boundary between the surrounding and then the system, this is we call it boundary line. And then we have also WF, it means the work results from the movement of the system boundaries. So for example, if you have piston, here I have the piston. So in this case, so this piston, right? So you have inside this pistons, I think I can make more clear compared than this one. Yeah. Okay. So like for example, like I have almost similar like the blue this curve, yeah. So here you have the out, this is in, this is out. So for example, in the piston, normally like there is such kind of the one tools that they are freely moving. So for example, like these tools, if you have the gas inside, so they will freely move. This is, we call it the kind of the tools like frictionless, yeah. They can moving like freely, it's depend on the gas. So in this case, like they will deform the boundaries like movement, yeah. For example, if you take the boundaries is it's in the line, this line, let's say like you have the boundaries in here, in the dash line. Then these tools, they will moving, go around. So they will deform the systems of boundaries. Deform, it means that they have the limit of the boundaries, like they will pass through. They will freely moving through the system of boundaries. So for example, the blue one, they can go to here, they can go to here, so they will deform. So the boundaries is not fixed, yeah, they can like passing through. And then in here, the equation for the WF, we can calculate for the workflow. Remember that dot, it represents about the flow, the same with this one. Equal to the F dl divided by dt. So this is force multiple by the, for the length total divided by the time. That's why here, like, because the piston is moving freely, so that's the dl itself is based on the length. Like for example, if I have these tools in here, a little bit here, of course the length is not fixed, right? So they are perhaps like it's more longer or it's shorter. So in this case, like the total of the work, it will be equal to the F multiple by dl divided by dt, or we can rewrite as the minus P dv divided by dt. So this is for the work, yeah. So then in the other side also dv in here, it's less than 0. That's why your work, it's larger than 0. So remember, like if you have positive, it means surroundings do work on the system. So in this case, if you have the gas inside your system, so this one is your system, and then the gas in. So when the gas in, of course, like the gas that moving this piston, yeah, moving this one, moving this is freely go to left or go to the right side. So when you have that dv is negative in here, this one, it's also negative. So you have negative, negative, it's become positive. So it means that surroundings do work on the system. So the workflow, the work of flow in and out for the open system, this is we can calculate by P delta V. So this is P delta V type, yeah. So it's depend on the delta V or dV divided by dt. So the same here, this is piston. Yeah, it's much better drawing compared than this. So if you saw that you have the pressure 1 and the outlet it's pressure 2, we can calculate the net workflow. It's coming from sigma. Remember, when you have the sigma, it means the total of the systems. So you have in and then you have out. So sigma mk multiplied by P delta V. So in here, because we gave the system is K, that's why we have the workflow for these pistons. Then other side, we have the energy balance equation. So this equation, it's very important. Please memorize. But I think to memorize this one is not difficult actually. If you see that basically the total of energy, it's include with the internal energy, kinetic, and then the potential, like we discussed in chapter 1. And then here, because accumulations, this one indicates the accumulation. So here you can write accumulations. Okay, so here you have the in and out, yeah. So in this case, you have the sigma mk u plus v power of 2 divided by 2 plus, we have here omega. So in this case, like you have the, for example, you have the u plus v power of 2 plus omega. So this is, it's coming from the out and in. Yeah, so if you have the system out and in, so this is, we call it, it's sigma plus q dot plus ws minus p dv divided by dt. So this is what we discussed before about wf, workforce. Yeah. So actually, if you have the total of workflow, it's coming from the summation ws plus wf. So later for the sign depends on the system. And then you have the plus sigma mk pv. So this term is so special. This system, it means that the pressure, its net pressure happens because of the flowing. So there is between the fluid flow and then the solid body, so they have the total of work. For example, you have the pipe like this, and then you have the fluid flow. So between the flow and then the solid from the pipe, this is also we have some energy. So here we can calculate by the mk PV. However, in the general case or general calculation, we can simplify the first equations. This is the first one, become the second one. So what's the second one? The second one, d divided by dt u plus mv power of 2 divided by 2 plus sigma. So in here it's omega, sorry. This is what for the systems. I said that this is not the sigma. It's we use the omega is much more easy because we have sigma here, right? So this you have the equal to the sigma mk h plus v power of 2 plus omega. So in this case, u plus pv, it's equal to the enthalpy. So you can rewrite thermodynamics identity. H is equal to the u plus PV. So U is basically internal energy, and the PV it's coming because of the fluid flow. They have the energy from the fluid flow and then to the solid of the cylinder. So this is what we call it H plus V power of 2 plus divided by 2 plus plus omega plus Q plus Ws minus PdV divided by dt system. Okay, until here. So we got the general equations for the second one. So remember that H is equal to the U plus PV. So it's not only for this equation, because we're going to use, even though later you study about the mixtures, so the identity for the enthalpy, it's the same. Yeah, H equal to the U plus PV. This is, we call it thermodynamic identity. So later, not only enthalpy, but also you have the energy Gibbs, you have also the Helmholtz free energy. And then how about the special cases in here? So for the special cases, there have some special sign here. For example, for the closed system. Remember, closed system, we don't have the mass in and mass out. It means the mass flow, it's equal to be 0, or m dot k equal to be 0. Or you can also rewrite dm divided by dt equal to be 0. So we can rewrite these equations. It means that everything relates with the m, it's equal to be 0. So we only have du divided dt inside the system plus m system dv power of 2 divided by 2 plus omega equal to the q plus ws minus pdv divided by dt. So we still have the energy flow inside the system. An adiabatic process, it means that the q dot, it should be equal to be 0, because adiabatic, it means like we don't have any energy loss. So here the heat, or the total heat flow, it's equal to be 0. How about the open steady state system? Open steady state system, it means that everything divided by dt equal to be 0. Why? Because steady state, it means they are not function of the temperature. So everything divided by dt, dm divided by dt, dv divided by dt, even the accumulation divided by dt, it should be equal to be 0. So you have open system, it means that you have mass flow and then you have energy flow. So that's why here we write 0, because here accumulation, remember steady state, it means divided by dt equal to be 0. So you have sigma mk, yeah, mk h plus v divided by power of 2 divided by 2 plus the omega plus q plus ws. Okay, so why in here like dv dt? Because it's steady state, so we don't have this term. We only have the q plus ws. Okay, until here I hope it's clear. Then we can go to the next. Okay, this is integrations. So how to integral the systems if you supposed to have the function of the t. This is interesting, like how we relate that the different form of the energy balance into the energy equations. So if you come back to here, you have d divided dt, u plus m mass, yeah, v power of 2 divided by 2 plus omega inside the system equal to the sigma mk h plus v power of 2 divided 2 plus omega. So in here you have the q plus ws minus p dv divided by dt. So if you take the integration of the t to t1 and then to t equal to the t2, so we can start to expand this equation, become u plus m v power of 2 divided by 2 plus omega at t2 minus at t1 equal to the sigma integral t1 to t2 for the enthalpy plus v power of 2 divided by 2 plus omega. So in here it's function of the dt plus q plus ws minus integral v at t1 and then to v at t2 p dv. So where the q in here, in this case, you have the sigma integral for the t1 to t2 q dt, and for the work also the same integral t1 to t2 is equal to ws. So this is how we integrations for the energy balance. So how you calculate later, it's also like depends. If steady state is not function of the t, but for the unsteady we need to consider about the time. Then after that, we have some several example that we use in the energy balance. This is one of illustration compressor operates at steady state. So I believe that in your textbooks you have the one question regarding this. So we can go to the page 54, yeah, in the textbook. So in this case, like, we would like to see that showing that the final result should not depend on the choice system. So in this illustration, like, we would like to know about when you choose the open system or closed system, is it the result will effect of your system or not? So we have the compressor. A compressor is operating in the continuous and steady state manner to produce the gas at the temperature T2 and the pressure P2 from 1 at T1 and then P1. Show that for the time interval delta T, the Q plus Ws equal to the H2 minus H1 delta M. So we would like to prove these equations according to different system. For example, like if supposed to be I choose the open system, can I get the similar equations if I choose the closed, like what happened with the calculation? So this delta M is the mass of the gas, yeah, mass of the gas that has flow in and out into the system in the time at the time delta T. Establish this result by the A. First, writing the balance equation for the closed system consisting of some convenient element of the mass. Then for the B question, writing the balance equation for the compressor and its contents, which is open system. Okay, the first one, we would like to define that the equation is actually a closed. So this is interesting actually, like what we're going to analyze that if you have the closed system. So in the closed system, because it's depend on the delta T, so then we can choose or divide into two different parts. Okay, this is, it means that combination, yeah, between for the compressors in this case. So we have here in and out, so P1, T1, and in here P2, T2 from this curve. So if you check, like we have in the middle, yeah, this is for the compressor. You have compressor because the compressor it's done by the shaft work. So you have the Ws. So in this case, like you cannot neglect Ws, and then you also have the Q. So and the system is closed. Remember that everything with the mass flow it's equal to be zero, but you have the energy in and energy out. The same, this is at T. So after several time, after T plus delta T, so in this case, we can write delta T. It means that T2, and then at T, it's equal to T1. And then after some time, and then you close the system, and then from the in, they become like out. So outlet, it means like from the compressor itself in the with the output, the second one, P2, T2. So then how we try to expand this equation? Remember that in this case, we have the M2U2 T plus delta T plus MC. MCUC T plus delta T, yeah, because in this case, we have, because the compressor itself for the T and then T2, or T and then T plus delta T, they are equal, they are constant. This one, the blue one, they are no change. The change is only with the 1 and then the 2. So here, you can write M, C, U, C at T plus delta T. It's normally equal to the M, C, U, C at T. They are equal. It means that the mass inside of the compressor, they are constant. Then we can write here, we try to expand first, MCUC T plus delta T minus M1U1, because here you have the M1U1 minus MC UC T equal WS plus Q minus P1 in here, V1 at T plus delta T, it's equal to B0, yeah. So in here at the second one, you don't have the P1 T1 minus P2 V2, because at P2 V2 you only have the at T plus delta T, but at T you equal to B0. Okay, I think in this case, like it's easily, if I try to expand one by one, because it's much more help in this case, I believe some of you perhaps is not clear yet, so I will use the assumption, start the assumption first. To make more easy how you define this one, you can use the closed system, and in this case, energy kinetic, energy potential, we negligible. So first, I try to expand d divided dt. You can start with the general energy balance. It's much more easier. Okay, so in here you have the u plus v power of 2 divided by 2 plus omega. So here you have the h plus v power of 2 divided 2 plus omega plus q plus ws minus p dv divided by dt. Remember, in here is closed system. It means that when you in at t, it means only you have initial. You don't have outlet yet. This is at t. But once you push the gas, they will move from the one, go to the second point. So it means at T plus delta T. So at T plus delta T, they have the compressor and then the second one. What you need to know in this case, like this is closed system, they are not continuous. And then it means it's only have the energy flows. Then we can try to integral this part between T and T plus delta T. So like we discussed before T2 and T1, we do the same. MCUC at T plus delta T and MCUC at T, they are equal, they are constant, so they don't change with the time. However, the inlet here and outlet, they are changed with the time. For example, in initial condition, you don't have P2 and T2. But at T plus delta T, you have the P2 and T2, but you don't have P1 and T1. That's why here we discuss M2U2T plus delta T plus MCUCT plus delta T minus M1U1T minus MCUCT. So in this case, T plus delta T, because they are constant, for the compressor, you can neglect each other. Why we don't have energy kinetic and potential? Energy kinetic and potential, normally we have, but the potential and then the kinetic, it's very small, so we don't need to, we can negligible in the system because they have a small effect. So that's why here we don't need to consider about the kinetic and then the potential. So it's equal to Ws plus Q minus P1, 0 in here, because at V1T at T, you don't have V1 at T plus delta T, right? So here it's 0. So remember, minus P1, V1T plus delta T is equal to B0, minus V1 at T, you have V1 at T. The same, minus P2, V2, because in the T plus delta T, you have the V2, but you don't have V2 at T. So multiple by M. Then you can rewrite the M2T plus delta T equal to the M1T, because they are actually, it's constant, yeah. So you have delta M, you can write, or MCUCT plus delta T equal to the MCUCT. Then in this case, you can write delta M U2 minus U1, because here you have the U2 minus U1 equal to Ws plus Q plus P1 V1 delta M, because here P1 V1 delta M minus P2 V2 del delta m, because here m you can replace with the delta m for the t plus delta t and then m1t. Then we can rewrite our equation delta m u2 plus p v2, because in here like the pressure is the same, so P1 and the same with the P2, or if different we can write the P2 here. Okay, so here we just try to indicate, and this one P1, so you have the delta M U2 plus P2 V2 minus U1 for the minus P1 V1, or you can try to rewrite the equation delta M, the H2 minus H1, so in this case you have the equal to Ws plus Q. Then remember that before we discuss about H equal to the U plus PV, similar case. So here U2 plus P2 V2 minus U1 minus P1 V1. So you can write delta M H2 minus H1 equal Ws plus Q. What you need to remember in here, if the pressure is not equal between P1 and then P2, you can indicate the symbol like in here P2, in here P1. So they will have a different meaning. So if you have the P is not equal to the P1, is not equal with the P2, so you can write U2 plus P2 V2. Or if they are equal, so it doesn't matter, you can write general P. Yeah, so this is just for the writing consistency. Then for the system open. Okay, so open, it means you have energy in, you have energy out, and you have mass in, you have mass out. So here is totally even mass and then energy, they are open. So what's the difference between the closed and then the open system for when we try to expand the equation? So for example, here you have the mass balance for the open, m T2 plus delta T minus mt, it's equal to the integral T to T plus delta T m1 dt plus integral T plus delta T m2 dt. It's equal with the delta m plus delta m2 equal to b0, or we can calculate by we can rewrite delta m1 equal to the minus delta m2, because delta m1 plus delta m2 equal to b0. So we can simplify delta m1 equal to the minus delta m2. So how about the energy balance? The same energy balance, we can try to rewrite the energy balance. U plus V power of 2 divided by 2 plus sigma, or plus omega here, minus U at T plus delta T, U plus V power of 2 divided by 2 plus omega at T equal to the integral T to T plus delta T. So for the M1, H1 plus V power of 2 divided by 2 plus omega dt, and then plus integral T to T plus delta 2 for the H2 plus Ws plus Wf plus Q. So this is, we just write all the energy balance first. Then you can assume that at steady state, because here like the open system, we can use the steady state for this case, because the flow it's totally continuous. So it means that the function, it was the steady state. So we can calculate the mt plus delta t equal to the mt. Yeah, for here, mt plus delta t equal to the mt. And then for the u plus v power of 2 divided by 2 plus omega. So in here equal to the u v power of 2 plus divided by 2 plus omega. So t plus delta t is equal to t, because steady state, it means they are constant, they are not depend on the time. Then it means that hi plus v hi cap plus vi power of 2 divided by 2 plus omega, in here I is don't change in the time. So the volume V is constant, because the volume, it means that because continuous, it means no change in the volume. So the V will be constant. So dV delta V, it will be equal to B0, or or WF equal to be 0. Remember, WF equal to the minus P dV divided by dt. So here is volume. So here if you have the constant, of course it's equal to be 0. Then we can write the equations from this. So we can neglect these two terms because they are steady state and don't change with the time. So it means that 0 equal to delta M1 H1 plus delta M2 H2 plus WS plus Q. Or we can rewrite here Q plus WS multiplied by H2 minus H1 delta M. So if you compare with the previous one, they are similar, yeah. Delta M H2 minus H1 equal to the WS plus Q, the same with this one. Delta M H2 minus H1 equal to the Q plus WS. So what we would like to comment in here, we would like to notice that the closed system analyzes that the surroundings are doing work in the system, yeah. So because the gas is doing work into the system at the inlet compressors, so while the system is doing works on its surrounding at the outlet pipe, yeah. So in this case, like surroundings doing work in the system in the in, and then the system doing work in the surrounding to the surrounding in the out. So because like if you check the compressor, the function it was we would like to increase the pressure. So the gas they will go in, and then the compressor they will push the gas. So in this case it means compressor do works into the system in outlet, but not in inlet. So then we can start to have the comments for this case first. Like for the open system, this work term has include the energy balance P delta V, multiple delta M term, so that it's become enthalpy because U plus PV. But PV in here is not from the PV of the workforce, but PV because they have the fluid flow. In open system, they have the mass flow, right? So once you have the mass in, so they will have energy between the mass and then the solid body of the system. So let me find the good definition for that. So this is, we call it net rate at which work is done on the system due to the pressure force acting on the fluids moving into and out to the system. So in this case, the pressure force is happen because of you have the fluid moving. So of course, this is always in the open system. But if you ask me in the closed system, do we have the pressure force? Of course, we don't have because you don't have the mass flow. Mass flow is only occurs in the open system. That's why for the closed system, we only have internal energy, but it's not for the enthalpy because we don't have the pressure force into the from the fluid moving. Okay, so and then these illustrations that the sum of the Q plus WS is the same for the fluid undergoing of the some changes in the continuous process. So then that's why in this problem we don't consider which is open, which one is the closed. The result, they are totally like almost similar. Yeah, if you can see like the first one, second one, they are actually like the same. Then Q plus W, it's different in the two process, but actually like it's depends on the how we try to expand our equations. So if you don't assume like it's a steady state, of course it's become different calculations, yeah. So in this case we have it was illustration 322. This is showing that the process in the closed and open system are different. Before we have similar case like open and then the closed system, they are actually like equal. We don't consider about the system itself, but in this case we consider that showing that the processes in the closed and open system are different. processes. It's not about the system itself, but for before, for the questions, it was we discussed about the final results. It's not shouldn't depend on the system, but here we discuss about processes. Then we have the questions like a mass m of the gas is to be compressed from the T1P1 to T2P2 in first one, a one-step process in frictionless piston and cylinder, or the big case is the flow compressors like the previous case. So here we need to assume that you have the open and then also the closed system. So what's these two difference? So for the closed system, let's say here I have the system, yeah, or I have the figure. So I can try to draw first the system, I think. So it's much more easier. So you have the closed system. So the closed system, it must have the piston like this. So this is the rod of the piston. So you have here P1, T1, and the other side we have another types of pistons, another kinds of piston. So the same here I have P2 and T2. Then the same, because piston, its principle is not because of the shaft, but it's because of the dV and then dt, because it's changing based on the total volume in the systems. That's why here Ws, I can write it's to be equal to be 0. So the Q, so we have here, I just give the dash line, this is Q. Then how are we going to solve this problem? So we start with the energy balance. Energy balance. So it means like we don't have no flow in, and we will start with the definition. You need to assume like what's kind of the assumption that you would like to state. In this case, we can state like no flow in and out. Neglect the kinetic energy and potential energy terms. So then we can expand the equation from the as the previous, yeah. If you still remember, we have the energy. So you can start with the, because this one is a closed system, so we can start with the du dt. So here I just write here first. I can write the more easy one. Okay, this is the energy balance roughly about the closed system. Du divided dt in the system plus m system, v power of 2 divided by 2 plus sigma equal to the q plus ws minus pdv divided by dt. So in this case, like you have the closed systems, then you can neglect the system according to your assumption. So here you can definitely just simplify as the total work. Okay, so it's makes more easy for you. So we can write here, because it's divide by the time, by the time, so or divide by dt, and then no flow in and out, only neglect the kinetic energy and potential energy. So we can rewrite that this is equal to the m u2 minus u1, yeah. So it's equal to the q plus w. So this is simplified for this equation. Then we can write the w, because it's not enough there, so I just write here like where W, it's equal to Ws plus Wf. So it's equal to, because we don't have Ws in this case, it's only have Wf, yeah. The previous I discussed, Ws is equal to, we define already, Ws equal to be 0. You only have Wf. So you can write here 0 minus integral P dV. So then you can rewrite your equation M U2 minus U1 equal to the Q minus integral P dV. Okay, so this is your equations for the closed system. It's not difficult, right? Then the next one, we would like to define if you have open system, like how it's going to be. Like actually, it's almost the same as like you discussed about the closed system, but here you have the energy in and energy out. You have mass in and then mass out. So let me try to draw the figure first for this open system. So we have here, this is open system. Then we can use the energy balance, like the Q plus W equal to the MH2 minus H1. So I think like we have the original equations like this. This is for the closed, but for the open, we can write again for the open systems. It was the from the previous like equation. So I will write again to make more easier to recall. So you have d divided by dt. Okay, so the same, yeah. So in here, because you have in and out, and then you have also the energy balance, so it's not difficult to expand the function, like how we going to calculate the result. So this, we have the Q plus W. Remember in here, I just try to expand this, and you can try to combine this one. It's equal to W. Because you don't have energy kinetic, energy potential, the same kinetic potential, so you only have in this case for the H, yeah, enthalpy U plus PV, but in here because it's enthalpy, so enthalpy H2 minus H1, and then it's equal to the Q plus W. So here, how about the dt? Because open systems, they are steady state. You can assume that this is a steady state. So I write in here SS. So please remember, like if I write SS, it means that the steady state. Steady state, it means that the flow is constant, so they don't change. So here we can, okay. So then you have in here the calculation, it's become H2 minus H1, so WF, because it's constant, so it means that you have minus integral P dV is equal to be 0. Or you can say that W is equal to Ws. Then you can use Q plus Ws equal to the M H2 minus H1. So in this case, this is your final. So what's the difference between the first case and then the second case? If you compare the first case, we have the W in here, but the QW in here is for WF, because we don't have the soft work in this case, you only have the piston and then the cylinder. The system itself, it's different. That's why you need to understand the principle of the equipment. For example, if you discuss about the piston and cylinder, we just we change between the volume. So it means that you only have the function of the volume with respect to the time. But if you discuss about compressor, it means we don't have WF because the WF was the dV divided by dt. They are constant in this case. They only have the WS because the compressor it's runs based on the soft work. That's the reason why in here we use WS. It's not WF. So if you can we can conclude that the Q plus W for the case A is not equal with the Q plus W in the case B. Okay, they are totally different. So we can comment this process when you have the process A or closed systems. So we have the process, we can try to simplify this one into to the evidence Q plus W. So in the other side, we can say or we can consider that we have the pistons. So in here to push into to the compressor, like illustration 3 to 1, yeah, like we discussed before. This is pistons. So you have here P1, T1, and then the gas it's go to the compressors and they will go out as P2, T2. So this is in the process A. So actually, based on the process, first inject the gas M into to the compressors or compress into to the inlet stream in the compressors. So here we have W1 is equal to minus integral P dV. So here you can write P1 V1 M. Then compress from T1 P1 to T2 P2. So using the compressor. So then we can get the Q plus W. This is W is for the compressor. So we can write the C. It's equal to the M H2 minus H1 all with the cap. Then we can get the compressor. How about we draw the gas M from the compress, refill the second cylinder or the second piston. We can write W2 equal minus integral P dV Okay, so then we can rewrite simplify for the withdraw the gas M from the compress and refill the second cylinder. So as you know that W2 here for the work equal to the minus PdV. Why? Because here is piston, yeah? We don't have soft work, we only have the work first. So this one is WF, here also WF. So the WS is only for the compressors. Then here we have the minus PdV. It's equal to the minus P2V2 because here we have the M with the gas M. So we can write minus P2V2 M, or we can use the cap, yeah, per mass. Then the total Q plus W for these three units with the works, yeah. So Q plus W equal to the Q plus W for the C compressor plus W1 plus W2. So in this case, Q plus W for the compressor, it's equal to the MH2 minus H1. So we write here plus P1 V1, it's in here because cap it's per unit mass, minus P2 V2. Then we can rewrite MH plus PV is equal to the U, the same H2 plus the P2 V2 is equal to the H2 for the U2, and then for the U1 it's equal to the H1 plus P1 V1. So remember H equal to the U plus PV, yeah, like the before. So if you would like to calculate for the U, it's coming H minus PV. So like the previous we write, I think in the H equal to the U plus PV, yeah, then we can write for the U is equal to the H minus PV. The same with this one, we can write H2 P1 V1, H1 also minus P1 V1, and then H2 minus P2 V2 is equal to the U2 minus U1. And then how about the others? Isenthalpic expansion. This is interesting actually. Isenthalpic, it means that H2 equal to the H1 or H1 equal to the H2. This is, we call it isen. Isen, it means equal. The same with the isentropic, S1 equal to the S2. The same with this one, H1 equal to the H2. Isenthalpic, this is, we call it. So we have Joule-Thomson. Joule-Thomson, it's one of the device that you use to expand. For example, like if you would like to release some gas and they have the isenthalpic expansions. This is, we call it the Joule-Thomson equation, is one device. The same like you withdraw the gas, but it's the gas inside, it was the high pressure. And then when you try to open the gas, and then it's suddenly like it's the gas is go out is so fast. This is, we can assume is to be isenthalpic expansion. Then in this case we have Joule-Thomson equations. So Joule-Thomson equations for the isenthalpic systems, this is we have in our illustration 3-3. Yeah? So the gas at the pressure P1 and the temperature T1 is steadily exhausted to the atmosphere at pressure P2 through the pressure reducing valve. So you can imagine like this is actually in the valve systems, and then there are isenthalpic conditions, and find an expression relating the downstream gas, the temperature for T2 to P1, P2 to and T1. And since the gas flow through the valve, it's rapidly, it's open so fast, one can assume that there is no heat transfer to the gas. So we can assume that the Q it should be equal to be 0. Also, the potential and kinetic, it can be neglected. So in this case, like we can use the assumption. This is assumption, the Q is equal to be 0. And then also no energy kinetic and no energy potential. So you can have the open system in this case. We can start to write the energy balance, D. Okay. Always write the energy balance. Even though you solve for the open or closed system, it's better to start from the general first. Don't go directly to the solution. You know, like in thermodynamics, sketch and then assumes and then start with the energy balance, fully energy balance, and then you can start to neglect the equation according to your assumption. For example, here we have the Q equal to be 0, energy kinetic and the energy potential terms are neglected. So this is the system itself. You can write it's for the valve, yeah, open system. That's why we write the energy balance for open. Then we can neglect everything here. So energy balance it means that everything, because it's open to phase, you can neglect this term. It's equal to be 0, the accumulation. Then you don't have energy kinetic, energy potential. Q also equal to be 0. And how about WS? And WS, is it FAF have the soft work? We don't have the soft work in the FAF, yeah? Because FAF is just to open and close, so you don't have the driving, the work is from the soft work, yeah, like a shaft or rod shaft to produce the work in your system, so you can neglect for the WS. And also because the V it's constant, so you can neglect the V, and then you only have here like MK and H cap. So you can solve in here with the K, with the M or with the K, because here you have N. So I just change in here, use the N. It's much more easier. N, because here is number of mole, yeah. So here I will put underline. Okay, so you can start to expand these equations. Use the 0 equal to the N1 H1 plus N2 H2. Don't forget to put underline because you have the mole, or you can use the N1 H1 minus H2, or you can simplify H1 at T1 P1 should equal to the H2 T2 P2. So from where this one? From energy balance or mass balance. So you can also try to expand. This is energy balance. For the mass balance also is possible to expand. It's much better actually when you solve, you can start with mass balance. It's better. So we can have 0, N1 plus N2, yeah. So you can write N1, it's equal to the minus N2. So you can write. So here, that's why it's become like this. Then, if the H, TP, so if H, T, and P for the T1, P1, and the P1 are given. For example, you have the enthalpy, and then they give you P2 are given. For example, P2 here, they give you the P2. So you can solve T2. You can solve T2, P2. You can know you can solve the T2. For example, like if I know that the T1, P1, and I know the enthalpy here, yeah, because they are equal. So then in the question, they ask about the exit temperature or T2. How much the T2? So if you know the H1, T1, and then you can calculate the T2. So we can able to calculate for the T2 because the enthalpy, they are similar. It's only different for the temperature, because in here you have the pressure and then you don't know the T2. So you can calculate based on the enthalpy. So one example for this is Joule-Thomson expansion GT, yeah, GT. And then the valve, this is one example, it's throttling valve. So if you supposed to be have the question, it's asking about isenthalpic expansion, there can be two ways. They ask for the Joule-Thomson or throttling valve. They are both are actually like it's mass isenthalpic conditions.